In section 9.4, we'll be learning about sequences. Sequence is an ordered progression, usually of numbers, that is separated by commas. For instance, 1, 2, 3, 4. In this case, we can call this sequence a finite arithmetic sequence. Finite because there's only 4 terms, not an infinite number of terms. The 4 terms are generically referred to as a sub 1, a sub 2, a sub 3, a sub 4. No matter what the first 4 terms are, that's what they'll be called. They say arithmetic, not arithmetic. And it's arithmetic because you would add or subtract the same quantity to get from one term to the next. In this next example, we have an infinite arithmetic sequence. It's infinite because of these 3 dots, which means it goes on forever, which the 3 dots are called an ellipsis. It's arithmetic because in the same way we would add or subtract, in this case subtract 2, to get from one term to the next. A sub 3, that would be the third term, would be 36. A sub n would be an equation which would allow you to figure out any term in the sequence. For instance, if n were 100, we would figure out the 100th term. As far as writing the equation for the nth term, we could imagine that because it's arithmetic, it's like linear. It goes up or down by the same amount. That's a linear progression. And so we could think, well, the first point's 40 and the second point's 38. 140, 238. Term number, term value. And we could then find the slope by change in y over change in x. We could write a point slope equation. This would be fine as long as x and y can be anything, all real numbers. But in this particular sequence, and in all sequences, our x value can only be 1, 2, 3, 4. So we don't use x and y. Instead, we replace the y value with a sub n, the value of the term, and we replace the x value with n, the term number. You could certainly use a point slope equation and this kind of logic to get yourself set up, but your final answer should have a sub n and n in it. We would often isolate the a sub n, so move the 40 over to the other side, or of course you could multiply it out and get something that looks like y equals mx plus b. The textbook will use this version, and in general it says that this 40 is the first term, a sub 1, and the slope is actually called the common difference to make the designation between a line and a progression or a sequence. And n minus 1 would always be constant. This formula can be used when you have an arithmetic sequence and you are looking for something called an explicit formula, and that would be like a y equals formula if we were talking about x's and y's, but in this case it would be a sub n formula. The reason it's important to call this an explicit formula is because there's another type of formula that you could use for this same sequence, and it's called a recursive formula. When you use recursion, that means you take one term and use it to get the next term, and then you use that term to get the next term. So you play off of the previous term. For a recursive formula, we need to say where we start, that our first term is 40, and then to get to the next term, the n plus 1 term, you would use the previous term, take away 2. Sometimes the next term has a sub of n plus 1, and then this is 1 less than it. Sometimes the nth term is used a sub n, so we could go either way. And then the previous term is 1 less than it. So it's the previous term, take away 2 to get the next term. Previous term, take away 2 to get the next term. As long as this is 1 bigger than this, you're okay. One more thing we should really do to be complete about it is we should give our domain of what n can actually equal. In this case here, our previous term can be a sub 1, so n could be 1. But you couldn't say that n is 0, because a sub 0, we have no idea what that equals to. But in this one over here, n has to be greater than 1. If n was equal to 1, this would be the term 0, but we don't have term 0, we have term 1. So the smallest n can be as 2, so it can be greater than 1. 2 minus 1 is 1, so a sub 1, 40, take away 2 to get to term 2, which is 38. Same up here. In every explicit formula, n would be greater than or equal to 1. So some people prefer this one because the domain is the same, and some people prefer this one just because they would rather shoot for a sub n because that part's the same in both of them. Last thing to mention is if you're using x and y, you're talking about a continuous function, a smooth graph, all real numbers. If you're using one of these equations here, you're talking about a discrete function, which means that n can only be integer values. So 1, 2, 3, 4, 5. That's what we'll be dealing with, so that's what your answers will look like. Notice there are 3 parts in the recursive formula: starting, how to get to the next term, and domain. And technically there are 2 parts in the explicit formula. And this is all for arithmetic. Now that we've found an explicit equation, formula, we could use that in our sequence, and after our 3 dots, we could put that equation, that explicit equation. It's sometimes referred to as the nth term, because you plug in for n. It's also sometimes referred to as the general term, or formula. So this is a full sequence. You could also represent that entire sequence, including the nth term, by putting the nth term by itself, or the general term, in these squiggly brackets, which is called set notation. This stands for all of these. So something else we can talk about regarding sequences is whether they converge or diverge. And we'll talk about diverge right here. First of all arithmetic sequences diverge. And the reason for that is this expression that we're going to talk about right here. And this is a very common expression when you get to calculus that you will see. In fact, sequences are a big deal in calculus. But this right here stands for these words: the limit as n approaches infinity. Limit n approaches infinity. For this set of numbers, and we can see that when you plug in infinity, actually you get negative infinity for your answer, not a positive infinity. You get negative infinity. And that is not a number. That is infinity. And so for that reason, we say that it diverges. If this had equaled 5, then we would have said it converges. Okay? So what you're looking for is the ultimate answer that this sequence approaches and gets closer and closer to. And then it would converge, but in this case it diverges because it's not a number. We're going to look at a couple different examples of sequences and talk about whether they converge or diverge and whether they're arithmetic. In the first case, this is a sequence, but it's very similar to the continuous function y equals 2x plus 1, 3x minus 4. That's something we're a little bit more familiar with. Does this have a horizontal asymptote? Does the y value approach a very particular y value as x gets to be bigger and bigger? And yes, we maybe remember the rule that if you have a rational function which has x's in the numerator and denominator, and if the degree of the numerator and denominator are equal, in this case x to the first power, then we can take the ratio of the coefficients, which is 2/3, and that would be the horizontal asymptote, which means that's where we are ultimately going. So we can say that this sequence converges to 2/3 in the same way as this function has a horizontal asymptote of 2/3. Remember, if the degree in the denominator is larger, then the horizontal asymptote would be y equals 0, and if the degree in the numerator is larger, then there would be no horizontal asymptote. and our sequence would diverge. In the next case, I have written the equation for the nth term, and then I can ask myself this question: what is the limit as n approaches infinity of 1 over n? Or I could put the squiggly brackets around it as well. Maybe I should do that. And I can see that when n goes to infinity, I'll have a fraction with a huge denominator, which means that my fraction's value will be 0. Huge denominator. So it converges to 0. This particular sequence has a special name. It's called the harmonic sequence due to something from music theory. So that's probably one that you might want to remember, and it converges to 0. Here are two other sequences that we could ask about: convergence or divergence. One that's a set of all numbers in the progression of cosine pi n. And this case here is a recursive formula, but it's called a second order recursive formula because I have to give two starting terms before I can use the recursive definition. I also can have to limit myself to n being only greater than 2. In the first case, when I plug in n equals 1, and the assumed domain for explicit equations would be n equals 1, 2, 3, 4, 5, 6, like that. So I get cosine of pi, cosine of 2 pi, cosine of 3 pi, etc. And as you can see, this results in an oscillating sequence of numbers. In the next case, my first two values are 1, and then to get the next value, which is n greater than 2, so that'd be n a sub 3, the third term, I would add the previous term, a sub 2, to the previous to that term, which would be a sub 1. I'd add the two previous terms together to get the next term. And I would continue to add the two previous terms to get the next term repeatedly, or recursively. And so 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. I get the Fibonacci sequence of numbers. For both of these situations, our sequence diverges. This one because the numbers get bigger and bigger till infinity, and this one because the numbers never settle into an answer. It bounces between two answers, oscillates. So in either case, we say the limit as n approaches infinity, as we get bigger and bigger and bigger, as n gets to be larger and larger, the limit does not exist. DNE is usually the abbreviation for that, does not exist, because we do not land on a particular value, in which case it would converge. Even bouncing between two values is not good enough.